All right, so now we start what might be called the theoretical part of linear algebra. The very concrete part is solving systems of equations, but now we're going to study vector spaces in general and functions between them, which are called linear transformations between vector spaces. So a vector space over the field of real numbers R is a set V whose elements are called vectors. And there are two operations on V. The first is vector addition. And the second is scalar multiplication. So the basic example, but far from the only example, is the one we've been studying most, which is the vector space equal Rn, the n-dimensional vectors, with coordinate-wise vector addition and scalar multiplication. But a vector space can be many other things. So this is the basic example, but what are some other vector spaces? Well, polynomials. Maybe even all polynomials of degree at most 2. So something like f of x equals a0 plus a1x plus a2x squared. We look at all these polynomials for all possible values of a0, a1, and a2. This is the vector space. I'll just write it as r square brackets x. This is all polynomials of degree at most 2. Because if you add two polynomials of degree at most 2, the degree can't go up. It can go down, but that's okay. The degree is still at most 2. And if you multiply a polynomial by a scalar, you get another polynomial of the same degree if the scalar is non-zero. So this is another example of a vector space. And what you really must do is study the text. And what we are studying in the book that I put on Blackboard is chapter 4 on vector spaces. So what's very important is the notion of a linear combination. So let V1 up to Vk be vectors in the vector space V. And let C1, C2 up to Ck be scalars. That are real numbers. So you can multiply a vector by a scalar and you can add vectors. You can take the vector V1 and multiply it by C1. Take the vector V2 and multiply it by the scalar C2, and so forth. Do this for all k of these vectors and add. So C1 V1 plus C2 V2 and so forth up to Ck Vk. This is what is called a linear combination. Of the vectors of each particular vector. We know what a subspace is in Rn. The subset W of the vector space V is a subspace if whenever W1 and W2 are in W, then W1 plus W2 is in W. Actually, there are three conditions. The zero vector is in W. The two vectors are in W, so is their sum. And if C is a scalar and W is a vector in W, then CW is in the set W. So the subset of the vector space that contains the zero vector is closed under vector addition and scalar multiplication is a subspace. Now there's a very simple way to construct subspaces. Let me just give you an example. Suppose we have specific vectors, say W1 and W2 in W. Sorry, in the vector space, please. Let W be the set of all linear combinations of C1 and C2. So we have two specific vectors, W1 and W2. And we look at the set of all linear combinations of them. And I claim W is a subspace of V. And how do I prove that? Well, first of all, 0 is a scalar. So if I take 0 times W1 plus 0 times W2, that's in W. But multiplying any vector by the number 0 is the zero vector. And adding the zero vector to itself is the zero vector. So the zero vector is in W. So that first condition is satisfied. If we have two vectors, let's say, suppose U is C1W1 plus C2W2 is in this set. And V is another linear combination, V1W1 plus V2W2 is in W. If I add U plus V, that's C1W1 plus C2W2 plus D1W1 plus D2W2. Just rearrange that. That's C1W1 plus D1W1 plus C2W2 plus D2W2. That's C1 plus D1 times W1 plus C2 plus D2 times W2. But the C's and the D's are just numbers, and if you add two numbers, you get another number. So this is again a linear combination of W1 and W2, so this is in the set W. So W is closed under vector addition. And if A is any scalar, then let's say A times V, that's A times D1W1 plus D2W2. That's A D1W1 plus A D2W2. A D1, A D2, these are just numbers. This is another linear combination of W1 and W2. That's also in W1. So the set of linear combinations of these two fixed vectors contains 0, the zero vector, closed under vector addition and scalar multiplication. So that proves this claim. W is a subspace of V. And the language used to describe this is that W is the subspace of V generated by the set S consisting of the two vectors W1 and W2. And we sometimes write W equals S with these angular brackets around it. That means S is a set of vectors, and W is the set of all linear combinations of the vectors in S. S generates W. You know, everyone has an intuitive notion that a line is one-dimensional. And the plane is two-dimensional. And box is three-dimensional. And one of the important achievements, if you like, of linear algebra is to give a definition of the dimension of something. How do you tell if something is one or two or three-dimensional? So the idea of dimension turns out to be based on something, two related concepts. One is linear dependence, and the other is linear independence. So we have a set of vectors, v1, v2 up to v sub k. These are said to be linearly dependent if there exist scalars c1, c2 up to c sub k, and this is the important thing. Some of them can be zero, but they're not all zero, such that if you take the linear combination, c1, v1 plus c2, v2, and so forth, up to ck, vk, you get the zero vector. So vectors are linearly dependent if some combination of them gives you the zero vector. So for example, suppose you let v1 be the vector 2, 1. And v2 be the vector 1, 2. And v3 be the vector 1, 1. If I take the vector 1 times v1 plus 1 times v2 plus minus 3 times v2 times v3, so this is a linear combination of v1, v2, and v3. It's v1 times number 1, v2 times number 1, v3 times number minus 3, but these are all non-zero. What do we get? We get 2, 1 plus 1, 2 plus minus 3 minus 3. When I add the vectors, I get 2 plus 1 minus 3, 1 plus 2 minus 3. That's 0, 0. That's the zero vector. So here I have a linear combination of vectors. Which is equal to the zero vector. So these vectors are linearly dependent. We say that the set of vectors v1, v2 up to v sub k is linearly independent. Well, the simplest definition is they're linearly independent for the set S if S is not linearly dependent. So if you take a set of vectors, maybe it's linearly dependent. If not, then it is called linearly independent. So any set of vectors is either dependent or independent. And a basic problem in linear algebra is given a set of vectors to find out which of the two possibilities it is. Another way of saying this is that S, which is the set of vectors v1 up to k, is linearly independent if whenever a linear combination of these vectors, C1, V1 plus C2, V2, and so forth, up to CK, VK equals 0, that implies that, in fact, all the scalars must be 0. So for a linearly independent set of vectors, the only linear combination that gives you the 0 vector is the trivial linear combination where you multiply each vector by 0. So for example, I take the vectors E1 to be 1, 0, 0, E2 to be 0, 1, 0, and E3 to be 0, 0, 1. The set E1, E2, E3 is linearly independent. Why is that? Suppose the 0 vector is C1, E1 plus C2, E2 plus C3, E3. Let's do the calculation. That's C1, 1, 0, 0, plus C2, 0, 1, 0, plus 3C, 0, 0, 1. When I scalar, multiply, and add, I get the vector C1, C2, C3. And if C1, C2, 3 is the 0 vector, then it means each one of these coordinates is 0. So the only linear combination of E1, E2, E3 that gives the 0 vector is the trivial linear combination with every scalar equal to 0. Let's look at another example. Suppose I take the vectors V1 equal to 1, 1, 0, V2 equal 1, 0, 1, and V3 equal 0, 1, 1. When you want to solve the problem, answer the question, is the set of vectors V1, V2, V3 linearly dependent or linearly independent? Which? Well, so suppose we take scalars C1, C2, C3, and R, satisfy the vector equation 0, 0, 0 is C1, V1 plus C2, V2 plus C3, V3. What scalars can satisfy this vector equation? This is C1 times 1, 1, 0, C2 times 1, 0, 1, C3 times 0, 1, 1. If I scalar, multiply, and add, I get C1 plus C2, C1 plus C3, C2 plus C3. Again, equals 0, 0, 0. So the scalars C1 and C2 have to satisfy the following system of homogeneous equations. C1 plus C2 equals 0, C1 plus C3 equals 0, and C2 plus 3C equals 0. So you learn from the first part of the course how to solve a system of linear equations. And it turns out when you solve these equations, the only solution is C1, C2, C3 all equal to 0. So it turns out the answer to the question, is this set of vectors dependent or independent? The answer is they're independent because the only linear combination of them, which gives you 0, is the trivial linear combination. So we now have two fundamental concepts in linear algebra. So we say that the set S generates a subspace W if W is the set of all linear combinations of vectors in S. And a set S is linearly dependent if and only if some sort of non-trivial linear combination of vectors in S gives the zero vector. That is, you can solve there exist vectors v1 up to vk in S and scalars c1 up to ck in R. Not all the scalars are zero with this linear combination c1 v1 plus c2 v2 up to ck vk equals 0. So these are two very fundamental concepts. The idea of a set of vectors generating a subspace and a set of vectors being linearly dependent, or if it's not, linearly independent. There is a fundamental theorem in linear algebra which says the following. I think I'm just going to prove it now and state it now, and I'll prove it in the next lecture, which says the following. That S be a set of k vectors in the vector space V that generates a subspace W. So W consists of all linear combinations of these k vectors. Let T be a set of L vectors in W. If K is less than L, what does that mean? If you have more vectors in the set T than you have in the generating set, then the set T is linearly dependent. So you have a subspace W and two sets, S and T, of vectors contained in W. The set S has K vectors, the set L, the set T has L vectors. And S generates V. If you have more vectors in the set T than in the generating set, the theorem says that the set T must be linearly dependent. So how does the proof go? So let's start with a simple observation, see if this works. If T is the vectors, let's say T1, T2, up to T sub L, contained in W. If one of these is zero, say T1, if T1 is zero, that means the zero vector, not the number zero. Then if I take the linear combination, 1 times T1 plus 0 T2 plus 0 T3 up to 0 times T sub L. If you multiply any vector times the number 0, you get the zero vector. This is all the zero vector. And if T1 is the zero vector, you take the zero vector, no matter what you multiply it by, it's still the zero vector. This is 0. And this is a linear combination of T1, T2, up to T sub L, but one of these scalars is not zero. So T is linearly dependent. So in any case, if the set T contains the zero vector, it's linearly dependent. So let's suppose that trivial case doesn't happen. Suppose T is different from zero for all vectors T in the set T. So now we do the following. It's a very tricky thing. And maybe I'll work this out in a special case. Suppose S consists of two vectors, S1, S2, and T consists of three vectors, T1, T2, T3. So S generates the subspace W, and T1 is a vector in W. So T1 is some linear combination, let's say C11 S1 plus C12 S2. Because every vector in W is a linear combination of S1 and S2. And T1 different from zero, because we're assuming the zero vector is not in the set T, means that at least one of these coefficients is zero. Let's say C11 is not equal to zero. So I have that T1 is C11 S1 plus C12 S2, and C11 is not zero. So what can I do? I can actually solve for S1. So I can say that C11 S1 is T1 minus C12 S2. And because the C11 is not zero, I can divide by it. So S1 is 1 over C11 times T1, this is a non-zero number, plus minus C12 over C11 S2. So I can write S1 as a linear combination of T1 and S2. Now I also know T2 is in W, which is generated by S. So T2 can be written as a linear combination of the vectors in S. Let's say C21 S1 plus C22 S2. And for S1, I can replace S1 by this expression. This is equal to 1 over C11 T1 plus or minus C12 over C11 S2 multiplied by C21 plus C22 S2. Let me just collect this. This is T2 is C21 over C11 T1 plus, and then I get something times S2. It's C22 minus C12 C21 over C11. So T2 is this linear combination of T1 and S2. Now, just to give them, just so I don't have to write these complicated expressions, then we call this, let's say, A, and then we call this B. So T2 is AT1 plus BS2. Now, if this B is zero, then A is not zero because T2 is not the zero vector. But then T2 equals AT1, or that's the same as saying AT1 plus minus 1 T2 is zero. This is a linear combination of T1 and T2, and I prove what I wanted to prove, that the set T is linearly dependent. So suppose V is not 0. V is not 0, we can solve this equation for S2. We get S2 times V is T2 minus AT1. Or if I divide by B, I get S2 is minus A over BT1 plus 1 over BT2. So now I get to the punchline that solves the problem. T3 has to be a linear combination of S1 and S2. So let's say T3 is, I don't know, xt1 plus y, xs1 plus y, s2. But s1 is a linear combination of T1 and S2. And S2 is a linear combination of T1 and T2. So if I substitute everything, I replace S2 by T1 and T2, the upshot is, and you have to actually work this out by hand on a big piece of paper, is that T3 is some linear combination of T1 and T2, which means the set T is linearly dependent, and that's what we wanted to show. So this is really very important. I only proved this special case, but let me just write down again the statement I just proved. So we have a vector space V. We have a subspace W generated by a set with k elements, k vectors in it. And T is a subset of W that contains L vectors. And if K is less than L, if there are more vectors in the set T than the generating set S, then the set T is linearly dependent. So there's an important concept in linear algebra called a basis. The set B is a basis for a vector space or just a subspace if W, if, first of all, V generates W, so everything in W is a linear combination of the vectors in V. And second, V is linearly independent. And now we can prove one of the most important theorems in linear algebra with a subspace W is generated by some finite set. Then all bases for W have exactly the same number of elements. So let me prove that theorem right now. As I say, before your very eyes. So let B1, consisting of the vectors S1, S2 up to S sub m, be a basis for W. Let B2, consisting of the vectors T1, T2 up to T sub n, also be a basis for W. So what do we know? We know that B1 generates W, and B2, because it's a basis, is linearly independent. Remember, a basis is a subset of a subspace that has two properties. It generates the subspace, and it's linearly independent. So B1 generates, and B2 is linearly independent. If B2 had more vectors than W, by the theorem, it would be dependent. So B1 generates and B2 linearly independent means the number of vectors in B2, which is n, is at most the number of vectors in B1, which is m. But now we can reverse the argument. B2 is a basis, so it also generates the subspace W. And B1 is a basis, so it's linearly independent. So this set has n vectors, and this set has n vectors. If n were bigger than n, this would be a dependent set, but it's independent. So therefore, m is less than or equal to n. And now we're in a very pretty situation. We have two positive integers, m and n is less than or equal to m is less than or equal to n. You put that together and you get m equals n. So this proves that all bases for a vector space have the same number of elements. And the name for that number is important. So the number of elements is the number of vectors in a basis for W is what is called the dimension of W. So the dimension of a vector space is unbelievably important in linear algebra and everywhere else in mathematics. And this is the definition based on the theorem. If you have a subspace of a vector space and you have two bases for it, linearly independent sets that generate the subspace, all bases have the same number of elements, and we call that the dimension. If a basis has just one element, it's a one-dimensional subspace. If a basis has two elements, it's a two-dimensional subspace. Let's look at a simple example. Suppose I take the line y equals mx in R2. That's my vector space. But as I'm looking at all vectors xy, which is x mx, so this is x times the vector 1m. So we know what that looks like. And geometrically, it's just the line through the origin with slope m. So this is my subspace W. And if I take the vector S1, be the vector 1m, S1 generates W. In fact, we can see it from this description. Every vector in W is a scalar multiple of this vector 1m. So the set V, consisting of just a single vector 1m, is the basis for this subspace W. So this line is one-dimensional because it has a basis consisting of one element. Suppose we're in R3 And in R3, we look at the XY plane. So this is all vectors with z equals 0. So this plane, let me call this W, it's all vectors x, y, 0 for any x and y. But I can write x, y, 0 as x, 0, 0 plus 0, y, 0. And I can write that as x times 1, 0, 0 and y times 0, 1, 0. Then we call this vector E1 and this vector E2. So this XY plane is the set of all scalar multiples of E1 and E2. So the set consisting of just these two vectors, E1 and E2, that generates the plane. And these two vectors, E1 and E2, are linearly independent. So here's a set with two elements that generates W that's linearly independent. So this is a basis for this subspace. How many vectors in the subspace? 2. So this plane is two-dimensional. The subspace has a basis with two vectors. It is, by definition, a two-dimensional subspace. Okay, well, in summer school, everything is intense and you have to go pretty fast. And so I covered a huge amount of linear algebra in this little talk. And we're going to spend a lot of time working problems to get a better understanding of this. That's it.